That's all I'm doing these days.
Very good. That's
Trying
the
to write,
That's the strategy.
Yeah, it keeps you sane, right? So it's all good.
Okay, so let's see. Share.
That's all I'm doing these days.
Very good.
Trying to write,
Second, that's the strategy.
It keeps you.
There's you saw some echo because of this the live streaming. 1 second. Sorry about that. I'll get back in there. I'll have to look at it for my thing. Very good. I trust my iPhone is my official timekeeper. Okay. Okay, so we can start. So thank you everybody to join us once again in the online SPICE and SPIN+X seminar series that I organize in collaboration with the SPIN+X Collaborating Research Center led by Martina Schliemann, Burkhard Hillebrand in Kaiserslautern, and Matthias Chloe in Mainz. As you guys know, this is a Zoom webinar, so please write your questions or in the Q&A or raise your hands. And I will let you ask questions to the speaker after the talk. If it's an important question, I will ask directly. Please check the schedule. We have it always at this time, but not every week. So please be aware of the schedule that you will receive, as you all know, the notifications every time that we have one. Today is a pleasure to have Vesna Mitrović from Brown University. She studied at Illinois Institute of Technology and Northwestern, and a postdoctoral in Grenoble National Lab. Then now is back in the States now. And she is well known for his quantum materials and NMR and quantum information science, and has several awards, but one of them, the notable, is the Alfred P. Sloan Fellow of the American Physical Society for pioneer contributions to NMR, a study at low excitations in emerging quantum materials, and she has some very nice results on how to look and think of quantum states, emerging quantum systems, and then I'd like to let me stop here and ask you to please go ahead and share your thing, your talk, and I will mute myself to give you more bandwidth, so I'll be monitoring the background. Okay.
Okay. Thank you for the opportunity to present here. So I'm actually going to talk today. You mentioned some of the quantum information science. So I just really want to talk about our attempts to really get to probe the ground state of quantum matter as close as possible. And, we all know that we were told that there's no magic tool that can actually just take a picture of the, quantum mechanical state. But let's see how close we can get to seeing what happens. And in particular, today, I choose one kind of simple sample since we are in a SPICE workshop. For example, to the question we ask, how does a wave function, ground state wave function, changes when a very simple system undergoes magnetic phase transition, of course, thermally driven. And anyway, I just really, before I start, want to thank our my student, actually, Ilya Nikolov, who has done a lot of calculations of this. Started with the postdoc Stephen Carr, Calvin Bales, who did most of the measurements, Dr. Adrian Rosuel, who is from Grenoble, joined us, and my colleague Ken Plum, who actually made the samples that I'll talk about, and Mladen Horvatić in Grenoble, who helped with some of the high field measurements that I'll talk about. So there's a messy slide here just to show you. This is what we have at our disposal. Our colleagues discover a new material, and then we usually start by doing these experimental probes. We ask, what is the crystal geometry? Is it insulator, conductor, and so on and so forth. So you refine your questions, your experimental probes become more peculiar. And then, of course, we use all that knowledge kind of to interconnect and help our theory colleagues build these models and these all the kind of techniques, a lot of approximative techniques, because things are just way too complicated. In the essence, what I want you to kind of understand that what we're doing is we are either probing excitations, right? Regardless of whether they are low energy or high energy or whatever, or we're looking at the response. You apply some bias field, say voltage, and then you see current, see how the system responds. And so in an essence, we get a very, quotation mark limited picture about really what this ground state is. And this is why all our most of the theoretical models describing the materials are kind of approximative. And so in 2019, when this paper came out, it almost seemed like science fiction. And we've been asking this question independently. Basically says, hey, imagine that I have some magic experimental probe. This is a ground state of my material. Can I actually, so I have to have some probe that it's locally coupled to Hamiltonian that describes my electronic state. And is there a way that I can actually perform a measurement of a single eigenstate? Because that's the only thing we can measure, and that can actually determine the Hamiltonian of my system. And, there's a fancy mathematics of QS that says maybe that's possible in certain circumstances. And really where the problem, why is it that we can, why is this so complicated? It works really well in quantum information where you have perfect, zeros and ones, perfect systems. Even then it's a problem because, the wave function, right, has this magic phase and we can only measure one of these eigenstates. And as I said, everything we do in conventional probes is, well, we probe, either these quasi-particles, so excitations, there's no guarantee that, say correlations between quasi-particles or entanglement between them is the same as the one in a ground state. So, and, again, we just measure linear response to some parameter. And regardless of, whether you really want to know ground state, maybe this is not important, but we do know we have numerous examples of materials where we have something that we call hidden order. And what that means is that, well, you measure some thermodynamic quantity, like specific heat here of this material, just say crystal structure or something. And you can actually, thermodynamically, there's a very clear signature of, say, phase transition. And then below this temperature where the phase transition takes place, there is a very well developed order parameter. However, that order parameter doesn't tell you everything because, if your state is, say, antiferromagnetic, like example here, you can then send again a probe and you get these, say, neutron scattering, and you get these peaks here. But if you have, say, now associated with this magnetic order, which happens, say, some multipolar order, as shown in this image here, if you actually repeat the same experiment, you will not get these red peaks here. And so we have a very clear thermodynamic manifestation of this phase transition, but then when we, again, depending on what we do, we might see or might not see the signature of this hidden phase. And that's the name hidden order. And so hopefully if we can actually probe, really this is the main motivation, the ground state and what's happening, can we actually find the hidden order? And as I said, there's a numerous example of where this hidden order emerges. And so to try to get, I actually choose a very simple material. So it's nickel, phosphorus, sulfur. So only 3 elements to actually study how can we actually probe a ground state. And so this material is van der Waals magnet. And it actually orders antiferromagnetically at 157 Kelvin. It's a very high temperature. You don't even need to go to a dilution fridge to actually probe ground state properties. And the reason why I'm showing this messy picture here is to say, well, because we only have 3 elements, people can do easily DFT, well, easily, quotation mark, not, it's never easy. And hypothesis that basically all of the orbitals are involved in the super exchange path that mediates this magnetic state below 157 Kelvin. So, and it actually has this antiferromagnetic order. It's the nickel spins that order. They are placed on a hexagonal lattice, and you see that you actually have 2 sub-lattices, which are antiferromagnetic with respect to this red and blue. And so we would really like to know how this hybridization of the orbitals that I have sketched here, how does that change once, magnetism ordered state is established? And I guess what we're going to use as a probe, so we don't want to shine any, pump a lot of energy into the system. So we want to do something that is minimally invasive so that we don't alter ground state. And for that reason, for our probe, what we actually do, we choose to actually probe. See, we have 2 phosphorus here, and we choose to actually do experiments on the nuclear spins of these phosphorus. And phosphorus is a beautiful nuclear spin of just 1/2. So the most quantum of all that we can choose objects. I just want to say that many of you, since everybody's working on magnetism here, might know that it's very easy to replace nickel with iron, cobalt. You can replace sulfur with selenium here, and you can profoundly change then the magnetic state. So there's a lot of interest in studying these materials. Also, what people have seen, if they cleave them, so if you lower the dimensionality, you can actually alter the state. So from technological point of view, it's important to understand what's going on, and so how can we design actually a device that we want ultimately to perform the way it's, we want it. So these materials have been studied with a traditional, as I said, nuclear spin of phosphorus is a very nice probe, and they're, if you want to study, say, a monolayer of that, it's very difficult to do that in neutron scattering. So this is why people have tried NMR, of course. And I just want to show you a static NMR, kind of traditional NMR measurements that have been performed on this material. So you don't have to know a lot about the technique, but this is NMR spectra as a function of temperature. And what we actually see here is basically a histogram of the local magnetic field that is produced by, these spins of nickel at this phosphorus site, okay? And things are pretty, we have a little splitting here that comes from the interaction of these 2 nuclear spins. And then as you cool down through this magnetic phase transition, what you actually see is significant broadening of the line. Now I have kind of 2 peaks. That basically tells me that, I have this antiferromagnetic environment, or, 2 different spin orientations. Okay, the NMR line broadens. As a matter of fact, we normalize these things just so you can see how much the spectra broadens. It's about 400 megahertz. 400 kilohertz. But if you actually don't scale it, you see how much you basically take your line and it just stretches out. So you have this huge distribution of the local fields. Not very informative. What one can also do is measure NMR relaxation rate. So how long does it take for your nuclear spin to spin flip and exchange that energy with the electronic bath? So if you're in the ordered state that it's gapped, what you should see is that it takes longer and longer time for nuclei to relax. So this rate becomes smaller and smaller and smaller. And yes, we can actually see this. We can, tell you basically what the gap is of this antiferromagnetic ordered state. At the transition here, if you look, there is nothing happening spectacular. And the reason being is that your Q vector of antiferromagnetic order is pi. So the nuclei, basically this information, if you look at these 2 spins, one is up, down, the other one is up, it cancels here. So you really don't see, you can gain a lot of information. So I'm going to go back to where I started. Oh, it would be so nice if I could do 1 measurement, okay? And that would inform me about the local Hamiltonian. And it seems that, if my probe is a nuclear spin, so it's very weakly coupled with electrons, which is actually cool. It will take you more time to actually, experimentally probe it, but that's not, that's just life. You always have to pay the price. And nuclei are coupled through this hyperfine interaction in these materials. And, as you can see, they are constantly talking. So basically, yes, the nuclear spin can actually change electronic state in a way. And then you can have these electronic correlations somewhere else speak back to the nuclei. So it could be a good probe. And again, we can use, what we can actually do is use what we call pulses or radio frequency to control the nuclear spin. And so what our proposal is not to look at the spectra that I showed you, this histogram of the local magnetic field, static image of that. But what we're going to do is actually focus on, can we actually monitor a phase that is accumulated during, time evolution that we can coherently control of the nuclear spin ensemble? Basically, I'm trying to do, this is something you would do if you try to implement very, in a modern parlance, this is called quantum control. So if you're actually trying to implement the gate with a high fidelity your qubit, that's what you would do, is this kind of, controlled evolution of your qubit or your spins. Now, remember that in this material that I talked about, we have spin 1/2, which is the most quantum of all. And, if this is my wave function at time 0, when I basically apply my pulse, set my clock, the evolution operator, so it's just fundamental quantum mechanics, is determined by the local Hamiltonian that your nuclear spin actually feels, okay? And what the pulses are doing, if I can just write the equation because it's so simple, it just rotates your spin, right? It's rotation operator about a particular axis that with respect to applied magnetic field. And so, this is just a different kind of quantum mechanical language of basically representing something that it's well known in NMR. It's spin echo. And I just want to show you, I'll go back to the beginning of my video here, what actually happens. So we apply what in jargon is called 90-degree pulse. Your spins are polarized. You flip it 90 degrees, okay? And then what these arrows kind of spreading out tells you that locally, each nuclear spin in your sample feels slightly different field. So they rotate, they dephase, okay? And then after a time, you leave the spins to, this dephasing is basically where you left them to evolve in time. And then after a time t, you apply 180, you basically invert the axis of time. You apply a time reversal pulse for magnetics. And then, they all come into coherence again. And that's what gives you this famous spin echo. And of course, they dephase afterwards. And that's a signal that you Fourier transform and you get the spectra that I showed you before, okay? And now I want to show you that what I want to do next is basically just take this experiment and see it in a slightly, different light, okay? So just to kind of repeat that we have these pulses that can rotate my spin. And then the time evolution, meaning you let your system just evolve, dephase. Each nuclear spin has a slightly different field that it feels, this hyperfine field, because it's in a different parts of the crystal, right? Anything it's super sensitive. So you have 1 part per million resolution to that. Therefore, any little, deviation of the crystal or any electron even moving around, fluctuating would give you a different phase that would accumulate or evolution. And so I want to go back to the material. Well, if I was to write what this local Hamiltonian, that is nuclear spin field, that is equal to, this is just a simple Zeeman term. You basically put your sample in a very strong magnetic field. And in addition to that field, there is also, right, the Zeeman, it's the field due to these electrons that order magnetically. But in addition to that, we have this interaction of this dimer, of this pair of 2 nuclear spins. And it's basically, you just write it, it's a square interaction of 2 spin 1/2 particles. And now I basically want to look into this Hamiltonian that nuclear spins feel. And remember that this is what controls your phase. And so this is a boring part, the Zeeman part, that if you remember all the spectra that I showed you, I told you NMR spectra measures a histogram of the magnetic field, internal magnetic fields. That really comes from this part of the Hamiltonian. This term is huge. If you put it in numbers, this energy term is, H bar is going to be 0 now. So it's of the order of, say, 100 kilohertz, okay? And now we have this interaction term. So we all know from, basic quantum mechanics class that when we have this is the first problem we do when we talked about interacting particles. The simplest problem to solve is to have 2 spin 1/2 particles interacting with each other. And what actually happens, you form these effective spin 1 state, okay? And this is the singlet. So this is spin 1 state, but the projection is 0 of this singlet state. And then we have a triplet state, right? And this is the interesting one that actually has the polarization. And it has these 3 states with the different projections, right, of the spin moment or MS quantum number. And so this is my state. And so the question is now, wow, if I can actually cancel this term here and just look at this red part here, or can I actually probe the properties of this spin 1 part of my, so now my phosphorus spin, suddenly all I want to do is probe the part that corresponds, that behaves like this. And that would allow me to actually directly measure this interaction term. And this interaction term comes from really the hybridization of the orbitals, s orbitals of this phosphorus spin, phosphorus atoms here. And how do we actually do this experiment? How do we, distinguish between the 2 parts here? So you can argue that, well, you can induce transitions between these states, but that's exactly what I don't want to do. I do not want to go into excitations and change field. And so, sorry. So this is what we are going to do. We're going to perform actually an interferometry measurement. And the way that why this works is that, well, remember RF pulse is nothing else but a rotational operator. And the thing that fundamentally distinguishes spin 1/2 from spin 1 on a most fundamental level is how it behaves under rotation. So we all have done at the beginning of in basic quantum mechanics that, well, if you rotate spin 1/2 for 2 pi, you actually acquire minus sign. That's all the really, quantum properties of spin 1/2 actually stem from that little fact. And that doesn't happen if you rotate spin 1, right? It actually rotates to itself after 2 pi rotations. And so this is what we're going to do. So my echo sequence that I showed you kind of in the old is actually allows me to construct an interferometer. And basically, there's our state, the wave function that comes in. You apply this pi over 2 pulse. So what that pulse does, and I'll show you in detail in a second, it kind of creates a superposition of all these states, okay? So it just creates a perfect superposition. It sets the clock in my experiment. And then we have these 2 paths they're really in the energy space, okay? So it looks like Aharon-Bohm spectrometer, except that I don't split my particle in 2. Here, we're really talking that we have 2 terms in the energy and they give me a different phase, okay? And so you see this term here, what would happen is as time flows here, is that, you let the system evolve. After the time tau, when you apply this pi pulse, that pulse does not affect this term here, okay? Nothing happens to it. It just continues through entire pulse sequence of time 2 tau. And basically, the net phase that it's accumulated is directly proportional to this interaction term here, okay? Where what happens with the Zeeman part, the blue branch, is that you evolve during the time tau. This pulse here actually inverts the axis of time, the evolution term. You see, now everything goes backwards in time. And so that whatever phase difference was accumulated here, it gets canceled over this process here. And so at the end of it, the sequence after the time 2 tau, you basically have a 0 phase here. And so your measurement, which is the echo magnitude here, is strictly proportional to this energy term. If you look at the magnitude, so you do not analyze spectra, you just look at the magnitude of your signal. And we said this idea, we thought it's so cool and new, but it actually turns out that people in group of Alex Spines in Berkeley, even in 1988, has proposed this, what they call NMR interferometry, to actually show that you can actually, when you have a system of spins that evolves in time, you can demonstrate that Aharonov-Anandan phase. So this is kind of a topological phase, very similar to Aharon-Bohm phase that accumulates when your system evolves. And you see what they have done is just to show the principles where they have this, what they call, how do I say this, circuit. So this just, there's, you have your pi over 2 pi pulse, and now there's a circuit. Circuit means I'm going to manipulate something. I'm going to apply a pulse that does certain things. And this was done on a very simple chemical, so more to show that this kind of phases exist in Hilbert space, where we basically taking this problem and turning it around. My circuit equivalent is my material. And now, I'm going to actually apply the sequence. I know what I should get to actually learn about, what interactions, what is my ground state of my material, instead of, trying to complicate things. And so let me just now walk you through very quickly through math of this to show you that, it's very easy to handwave, but this is such a simple kind of mathematics to show that indeed you can, the only thing that that you indeed get interference, and that you can just observe the magnitude of this echo and directly extract this interaction term, interaction frequency. And so, as I said, we apply this first pulse, pi/2, and this is that pulse. Actually, at time 0, just creates the superposition of the states, so triplet of these three states with different projection of the spin quantum number in this effective spin 1 manifold. And then your Hamiltonian acts on it. And it turns out that if you apply this Hamiltonian, that's going to control your phase of time evolution of your states. This particular state has no magnetization. Its projection is 0, and therefore it's absolutely not affected. So this is your reference, actually, a beautiful way of defining a reference for your phase of your interferometer, where these two plus and minus states, or plus and minus 1 states, if you write the math of that, you apply this Hamiltonian, this interaction term here, you see that this is how it would evolve in time. You have two frequencies here, interaction 1, and then, of course, the Zeeman frequency, okay, after this pulse that controls. And now we're going to basically, okay, apologize for that. What we're going to do now is we have this pi/2 pulse, and then it evolves for the time tau. So all I have to do is just rewrite this equation, just to kind of have the whole system here, how you show that this doesn't evolve in time. And now the time comes where we apply this pulse. So there's, again, I'm just gonna, this is where we are in time. And now we're gonna apply the pulse, which again rotates about x-axis, everything. And what that does, it actually changes the sign. You see what happens, okay, here, is that the only thing that this pulse does, it actually changes the sign of the Zeeman term. Here it's plus, and here is minus. And if you leave that system to evolve another time too, these Zeeman terms will cancel. And this is what I obtained, that my state after time 2 tau is basically, we have our reference that the 0 state did not change. And I have these two terms that are now acquired absolutely the same phase. You see, minus 2i omega it tau. Same phase is accumulated here. And now, you can actually view it, as I said, our interferometry in the energy space, where this is my reference, this state 0. This state 1 evolved. You see, these two states evolved in a different direction. This pulse inverts that, and now we just have to combine them all. And so, and then obtain their interference. So what is this magic combination? It's my measurement. So the way we measure this, we have a coil, and we measure the signal inductively. And the coil is always perpendicular to the applied field. So quantum mechanically, my signal is basically proportional to the expectation value of my state, which is here, that we involved, and sandwich between I plus operator. Okay, IX, prefer to use this. So if you write this, again, just the simple mathematics, there it is. This is your end result. That's what you actually measure. The amplitude of your signal that you detect, the inductive signal of this spin echo, would oscillate as 2 times omega of this interaction term times tau. And so what that basically tells us, that if we, if I record the amplitude of my signal, I would actually be able to directly measure this. And so let me actually show our results. So everything I showed you before, this kind of traditional NMR, was done by taking a spin echo, Fourier transforming, and then you get the spectra. And that's information about this term here. That's really what you observe. And then what we're now doing is just looking at the magnitude of the signal as a function of this time tau, okay, arbitrary units. This is my time. And you can see this is just a zoom at these frequencies as you're approaching, as you're going through this magnetic transition, and you see these beautiful oscillations, okay? And then these oscillations can directly allow us to extract this interaction term. Now, everything I told you so far is I just, dealt with one single spin. It turns out that, of course, your sample is ensemble of nuclear spins, which is actually really cool because, each spin can actually feel slightly different interaction term because of whatever, some strain in a lattice, right, from side to side. And so we can actually, this is if you have any variation in this quantity here, that's a very definition of decoherence. And if you actually pay attention to these curves here, you see that the amplitude, it's not just that there is a frequency, but the amplitude actually dies out. There's an envelope, exponential decaying envelope, and that actually comes from the variance in this variation in this and that term, basically decoherence. And we can separate these basically decoherence terms. So just to show you that, now if you do the whole, full theory for ensemble of nuclear spins, you basically obtain that, again, these oscillations of the echo. And if you pay attention that this magnitude of these is dying out, and that comes from, again, as I said, that you could have the variance, not just that this term is not constant, it is for a single pair of spins, but if you move in a lattice, if something changes, you can actually have a very high resolution on what what this variation of this term is. And as I said, that's a very definition of coherence. So we have two terms that contribute. As I said, you can have variation of this term, and you can see it causes exponential decay of your of this frequency of this signal. And in addition to that, you can also, we always have in this Zeeman term, so the local field itself is different, and it causes decoherence. This is very well-known T2 kind of in jargon. And that's what actually causes your echo signal that I showed you in that video to actually dephase out. And that kind of multiplies all of this stuff here. So again, we can, if you think about it, there are some terms here, if you do the mathematics correctly, which basically tells you that your, how do I say, the contrast of these interference fringes of this oscillation actually depends on how much of this term you cancel. And so if you change this angle here, the tip angle, you can, vary the amplitude of this signal and kind of convince that you really know what you're doing. You can change the contrast if you're in your interference. And so let me now show you, once you actually analyze these amplitude fully with taking into account all these effects, what is the net result. And first, as I said, I was saying that if we change this pulse, so for example, if this is not pi, but I put pi over 2, I will not cancel this term. And you can see here that this is our data when we actually apply 4590, that the amplitude actually of this oscillation is significantly lower. So it's this pulse, or the strength of this pulse, that controls the contrast in your interferometer. So you can, these are just different measurements of, you can see how the amplitude oscillates at one particular temperature. And of course, the 90-180 gives you, it completely cancels this magnetic term. So it gives you the highest contrast, and you can see the highest amplitude of these oscillations. And then as you go to 45, you can suppress completely if you tune your pulses correctly. Okay, and then let me just show you now the result of all of this. So what I'm actually plotting here is that you analyze as a function of temperature here, okay? you basically analyze this interaction term. And what we see that from room temperature down, as you can see, this is the frequency of this interaction term. It's actually 2.6 kilohertz. You can resolve this no problem because, you know, it's very easy to obtain frequency. Remember that our NMR spectra is, you know, hundreds of kilohertz. Yet you can resolve this interaction term of 2 kilohertz because it's really interference. It doesn't depend on the spectral resolution. And so, interestingly, we have this one value of interaction term in paramagnetic state. And then, as you come to this transition region, I'm going to zoom into this. You see that this interaction term drops down. It drops about actually 40%, 30%. And then it actually, now we acquire a new frequency that, you know, from 150 Kelvin down to, I only have it here shown to 40, but we did measure down even to 3 Kelvin, does not change. And as a matter of fact, even checking these results as a functional field it does not change this number. And so let me just kind of walk you through this, that we see this huge jump in interaction term or change at this magnetic phase transition. Come back to what it means. But before I go there, I just want to point out that the only thing that we measure, the amplitude of our signal strictly depends on the phase. It does not depend on excitations or, you know, the field that it's created in the sample. And so this temperature is actually this measurement is completely insensitive to temperature variations. It does not depend and so not surprisingly, you actually see that this interaction term is temperature independent in both phases, in paramagnetic, in antiferromagnetic phase. If you zoom in into this transition region, what actually you can see here is that what I plot in this inset is the weight of this. So there are actually 2 frequencies in this region. You can actually see it with the bare eye. And if you actually look at the weight of that, it's almost, this looks like the other parameter, but it's not at all. So this is, as a function of temperature, we have a weight of this, you know, interaction term from antiferromagnetic state, and you see how it actually increases to reach 1 below 152 Kelvin. And then at the same time, you see this paramagnetic, the interaction term that corresponds to paramagnetic phase, how it actually decays here. And what is very interesting is that, as I told you, that we can actually measure this, also the distribution of this term. So in the paramagnetic state, this is what I'm showing you here, this gamma term. In a paramagnetic state, this term is 0, which, you know, it makes sense. So imagine that we have an interaction term. It's actually quite boring in a paramagnetic state because, you know, everything is fluctuating, everything averages to 0. And so not surprisingly, this interaction term is nothing else but the classic kind of, if you put the numbers in, you can actually recover that it's exactly 2.6 something kilohertz. It's a dipole-dipole interaction of the nuclear spin. So it's quite boring, as a matter of fact. And you see that this variance of that dipole-dipole term is 0, okay? This gamma term. And then it jumps up. And in the ordered state, actually, this is just to show you actually how big this variance is compared to the absolute value of this interaction term, that in the ordered state, this term is actually 1 kilohertz, which is, you know, this is 1.8 kilohertz. So it's almost, the variance is almost twice the mean of this interaction term. And so the way I like to kind of think about this is that what this measurement allows you to do, right, is to actually measure how the ground state wave function changes as your system undergoes magnetic phase transition, which of course is thermally driven, but your measurement is completely blind to thermal excitations. And what is very interesting is that you see that in the ordered state, this interaction is actually lowered, and it has this huge variance. And the way you can actually think of this is that there is a, you know, if you think about it, we have magnetic correlations now, it's almost like the orbitals had to move to mediate this magnetic interactions on these hexagons of nickel here. And so it's almost as if the hybridization between now phosphorus is actually weakened by pulling these d orbitals, or actually, should I say, these p orbitals that mediate the magnetic interaction in this term. And because we have, as you can see, these two kind of paths, two different orientation, not surprisingly is that in the ordered state, we see these variants that it's almost half the value of this interaction term below the transition temperature. So with that, I just want to basically say that hopefully what we measured actually can be really input for first principle calculations that can actually really guide them, because these are real numbers and it would come out through DFT calculations. And it actually shows you how, your wave function with calculations, it should directly tell you inform you how the ground state wave function changes through this magnetic phase transition. So anyway, with that, I would just like to, again, acknowledge help from our team. And, I'll stop here for questions.
Yeah,
it's right on time.
Well, thank you. That was Vesna. This is very nice. For me, it actually brings lots of memories, because my thesis was on studies on the quantum Hall effect using NMR.
Okay, good.
So this is a very, very powerful tool, when you talk about quantum echo and spectroscopy. So we have the thing. This is a bit of the topic that is usually not so much covered here, which is actually very useful for some of them to see. So I'm not sure if the Q&A is going to be so active. I'll please raise your hands if you would like to ask a question to the speaker. I'll start a little bit by a quick question that I was thinking as you were studying this particularly being able to also see the particular orbitals. In terms of trying to do, because it's spectroscopy, you're doing a spectroscopy and the interference, but what about in terms of length scales, particularly magnetic systems, which are useful for us, that we're interested on? Sometimes they have a lot of domains. Is there a possibility to do some sort of length scale probing the different areas?
Unfortunately, it's a histogram, right? So you get the local information and then it's an ensemble average. Mm-hmm. Now, if, it is possible through this kind of measurement of this quantity here. So mm-hmm. Say if I had, I really don't know where this comes from, and it could be, the easiest thing to say now without doing, complicated calculations, it comes from a strain that it's induced by having, you have this sublattice, which is oriented in one direction, and then this one in this direction. And is it possible that it comes from there? But again, if you have domains, you will see, again, in this quantity which show, which spectrally you could not, it would just broaden really too much, but you will be able to get it through some simulation, what these domains are. And the question is, do I have two domains in my sample? Do I have, many? There are some tricks that you can play, but it's, in principle, it's funny. It's a microscopic technique, yet it's bulk, right? Because you do get information from this ensemble average. So it really depends how much you can say. We don't have a length scale, but it depends on really what the system is and what the physics is. So in principle, you have some,
and also from the perspective of dynamics, if I wanted to actually study, maybe you cannot move it with magnetic fields. In this case, we'll screw up your NMR. But say you have a strain system or something where you actually are able to dynamically move some of the domains, and that will change your spectra dynamically. In terms of the scales, have you looked at in terms of if you would have to be stationary, or can you actually be close to that?
This measurement is static in a sense that measures whatever happens, during this tau, which is usually, say on a time scales of hundreds of microseconds to a millisecond.
Yeah.
And so what, depending on a system. So for example, if you were to apply a strain and do whatever you want to your system, right? Drive it by voltage or drive it by, I don't know, some kind of radiation, or it's just a strain that you apply a pulse and then say that things would move. So yes, you could maybe do that where you measure the relaxation rate. But if I don't want to measure relaxation rate, the question is, how fast does this thing relax? So for example, in a micro,
I think the scale would be too fast of
yeah,
relaxation
that would be too fast. So this
in this case, it's
as static as you
too
get.
many orders of magnitude difference.
Yeah.
It's more of a move it, measure it, move it, measure it type of.
The question is, if you move it, what are you really changing, right? Are you just sliding some order, or are you actually really changing the order itself?
Yeah, that's where the modeling and the particularly
Yes,
what we're all thinking nowadays. So I'm quite busy thinking of these unconventional magnets, of these anisotropic magnets, anisotropic ordering, looking at altermagnets and P-wave magnets and things like that. It would be interesting to see what type of NMR signals one gets in such systems, because there you have a strong anisotropy connected to the crystal direction. And this is something that would be interesting to add in there probably in the analysis, because this should actually have an interesting signature, I would say.
Yes, and depending on it is an isotropy would, and it would be interesting to see what kind of materials so that we can plan.
Right now it's in quite a homogeneous system. Very good.
This was the simplest of all. It's just very easy to kind of illustrate the technique. It's a very simple. I mean, there's a lot of interesting physics questions to answer, but the system itself is just very simple to kind of illustrate.
So I don't think, it says like I see Peter and I see other people in there, but they're not asking questions. So maybe I just try to digest all the stuff. For me, I'm familiar with the NMR from long, long ago. This is, I don't want to say how long, because then I confess my,
it was my postdoc also, gallium arsenide.
Yeah, this is something that, I loved for a long time, when you say SPIN+X, it was, warm to my heart. But it's a wonderful new tool. Well, a new tool, it's an old tool, but also discovered in a new way that I think is useful, not to forget the power of these tools and how to reinvent them and really re-examine many of these complex, both magnetic and electronic correlated systems. I mean, in many systems, I mean, it was the tool that came back to Texas A&M right now for these weeks, where David Lee moved and stayed the rest of his life, still here. We're discovering helium-3 with NMR, the NMR being so fundamental for quantum Hall effect and functional quantum Hall effect in particular. So yeah, it's wonderful to see. Yeah. Okay, so I don't see any other questions, which puzzles me, but sometimes, I think it's the week before Thanksgiving or something, or the day before Thanksgiving, people are still relaxing.
Yeah.
But I really thank you for it's so pedagogical that you've given this talk. Oh, hang on, there's a person, maybe. Okay. About the panelist, Banan El-Kerdi. Let's see if he can ask a question. I think he's rejoining. I don't see rejoining, but maybe to talk, maybe. Okay. So I don't know if you're rejoining or not, but you can ask a question now. You have the microphone. You're allowed to ask your question, Banan. Okay. Banan, okay. Okay. He raised his hand, but I'm not sure if he's asking the question. Okay. He's unmuted. He's muted still.
Hello?
Yeah, go ahead, Banan.
Can you hear me?
Yeah, we can hear you.
Thanks for the nice talk. It's really impressive work. So my question is, by NMR, it seems that you are measuring the bulk, right?
Yeah.
So can we measure thin layer within the NMR technique?
There are tricks to play. Yeah, that would be our next step.
So how do we do if so we can? What is the tricks?
You can play tricks with the microsurface coils. So that's to get, the problem is you cannot use the classic kind of solenoid coil. So there are tricks that one can play to try to get to, thin films, layers. So the problem with right now that we're having in material exfoliating, because you can do it like graphene, exfoliate this.
Yeah.
Problem is that controlling where the flake goes and putting it right on your coil, on your surface coil, it's really, really, really difficult. So that, it has to be practiced. Maybe look at the thin films actually instead of monolayers, because yeah, the Scotch tape does not work as well, or it's not as controllable here as in graphene, so, or not perfected that well. So
Okay, thanks.
And the problem with the Scotch tape is, as you can see here, in graphene you have a p orbital, so it's very easy to cleave it and place it where you want. Electrostatically here, the d orbitals are messing you. So yes, you can cleave it very easily. It is van der Waals material, but where your things go, it's important. Yeah, but there are tricks to play with these surface foils.
Yeah, and then, well, if you're interested, maybe contact Vesna and then work on that.
Yeah.
Yeah, for sure. Thanks.
Thanks
Or if
a
you
lot.
can make a device controller, yeah, that would be great.
Very good. So I think on this, I'm going to stop the streaming, and streaming, and then great.
Thank you.
And I think all there were 60 of you that watched it live, and then the rest of